Today we are taking Brønsted and Lowry theory to the next level by looking at what conjugate acid-base pairs are, and then doing some practice questions, and then we're going to finish up by looking at things that can be both. And as always, you can find this document, a free to download PDF, in the description, so make sure you have your own copy so you can be making some notes for yourself as we go through. Alright, but before we look at pairs, we just need to quickly remind ourselves of a few things. So thing number one is our definition for acids and bases, to do here with proton donors, proton acceptors. And then thing number two is that reversible reactions happen in both the forward and reverse directions. So they happen in, both directions. So now we have remembered that, we can easily understand what a conjugate acid-base pair is. So if we have a look at this example here, we should be able to figure out what is going on. Okay, so in the forward reaction, the ethanoic acid is acting like an acid, as it is donating a proton, and water is acting like a base, because it has accepted that proton. However, as this is a reversible reaction, if we go the other way, then the opposite is true. So in this case, the ethanoic ion is accepting that proton and is therefore acting as a base, and the hydronium ion is acting like an acid. And everything is kind of linked together, paired together via a proton. So the ethanoic acid and ethanoic ion are paired together, as is the water and the hydronium ion. So the only difference between the pairs is a proton, is a hydrogen ion. So this is leading us to our definition. So a pair of species differing by a single proton is called a conjugate acid-base pair. And at the start, the ethanoic acid is acting like an acid, it's donating a proton, and the ethanoic ion is called its conjugate base. Water is acting as a base, and then it's paired up with the hydronium ion, which is acting as a conjugate acid. Okay, hopefully that makes sense, but if not, let's look at some practice questions to make sure we fully understand what is going on. So with these questions, I always just like to pair things up with things, with what looks similar. So that looks similar, and these look very similar. And then once you've figured out the things that look similar, we can see which is the acid and which is the base. So if we have a look at these two, first of all, we can see that a hydrogen ion has been lost. So therefore, this must be our acid, and then conjugate base, and then via a process of elimination we must have our base and then conjugate acid. So we'll do the same nice and quickly for our other example. So again, what looks similar, let's pair that together, and then we can look at what's going on with hydrogen. So we can see here we have lost a hydrogen, so therefore this must be the acid, conjugate base, and then over here we can see that this has gained a hydrogen, so this must be the base, and then this is the conjugate acid. And our final example, again, let's just highlight the things that look similar, and if we look a little bit closer, we can see that over here we do have two acids. However, one acid is stronger than the other. So with this, the sulfuric acid is a much stronger acid and is acting like an acid, because we can see it's lost a proton, and the ethanoic acid in this case is acting as a base because it has gained a proton. There we go. Okay, now finally onto what it means to be amphiprotic and amphoteric. So we have the same equation as we had earlier, and we're going to be comparing it to this equation, as both of them have water in. So in our first equation, we've got water, and water has gained a proton, so therefore it has acted like a base. In this equation though, water has lost a proton, so therefore it has acted like an acid. So something that can do both, so a species that can do both, can be both a Brønsted-Lowry acid and a base, is called amphiprotic. So something that can both donate and also gain a proton is amphiprotic. Yeah, okay, and now on to our last word. So our last word is amphoteric. So here we got, so zinc oxide is an example of something that is amphoteric. So amphoteric are species that can react with both acids and bases, but however, they don't have a proton to donate. So in our first reaction, zinc oxide is neutralizing an acid to give us a salt. And in our second reaction, it is reacting with a base, neutralizing a base again to give us a salt. Happy days, there we go. Okay, so that's everything from me today. But yeah, if this video didn't go into the level of detail you were after and you need more things explaining chemistry-wise, then check out my website. The link is in the description, and there you can find out more about chemistry tutoring. And yeah, thank you for watching. That is everything from me. But yeah, please do like and subscribe, and yeah, I will catch you in the next one. Ciao.